Here is a strange pair of facts that sit oddly next to one another. In a few rare corners of the universe, gravity becomes so overwhelming that it folds space into a pit nothing can climb out of, not even light itself. And yet, taken as a whole, that same gravity appears to be losing. The great islands of stars we call galaxies are drifting apart from each other, and the drifting is not slowing down the way you would expect. It is speeding up, pushed outward by something physicists can measure with real precision and cannot explain at all. Tonight, we are going to sit quietly with both of these mysteries, the inward pull and the outward push, and notice how they grew out of the very same handful of equations. Before we begin, I would love to know where in the world you are listening from and what the clock says in your room right now. Leave it below if you feel like it. And now, let your shoulders fall and let us take all of this very slowly. Let me start again, more gently this time, because there is no rush at all. You do not need to understand anything tonight. That is worth saying out loud before we go any further. You do not need to follow every turn. You do not need to remember a single name or number, and you certainly do not need to arrive anywhere. This is not a lesson you will be tested on. It is more like a long, slow walk through a part of the world that happens to be made of stars and space and time, taken at a pace where nothing is hurried and nothing is left out for the sake of speed. If your mind wanders off in the middle of a sentence and drifts away into sleep, that is exactly what is meant to happen. The words will keep going without you. They will still be here, murmuring along, whether you are listening closely or only half hearing them from somewhere near the edge of a dream. So settle into whatever position your body wants. Let the weight of you sink down into the bed or the chair or the floor. There is a whole evening ahead of us, and we are going to spend it on two of the strangest things anyone has ever discovered. And we are going to spend it without any tension at all. Let us begin somewhere very ordinary, because almost everything strange in this story begins with something you already know in your bones. Think for a moment about dropping something. Not on purpose, just the way it happens a dozen times a day. A spoon slips off the edge of a table. A book slides from your hand as you fall asleep reading. A coin rolls off a counter and rings against the floor. You have seen this so many times that you no longer see it at all. Things fall. They fall downward, toward the ground, and they fall whether you want them to or not. A child learns this before they can speak. You hold a rattle over the side of a high chair, you let it go, and it drops. And somewhere in that small, repeated game, a person works out one of the deepest truths there is, long before they have any words for it. The world pulls things down. Now hold that ordinary feeling in your mind, and let it grow very slightly stranger. The same pull that takes the spoon to the floor is the pull that keeps your feet on the ground when you stand. It is the pull that keeps the air pressed against the surface of the planet, so you have something to breathe. It is the pull that holds the moon circling above us, and the pull that holds the whole Earth swinging in its long, patient loop around the sun, year after year, never flung away, never falling in. It is all the same thing. The force that tips a mug off a table and the force that arranges the planets are not cousins. They are one single thing wearing different clothes. And that single thing has a plain old name. We call it gravity. For most of human history, that was where the story comfortably stopped. Things fall down because that is simply what things do. But somewhere in that quiet word, gravity, two of the most disorienting ideas in all of science are hiding, waiting, and they pull in opposite directions. One of them takes that downward pull and turns the dial all the way up, past anything you could imagine. until it becomes a place where the pull never stops. A place we now call a black hole. The other takes the very largest view, the view of everything at once, and finds that something out there is pushing the opposite way, gently shoving all of space apart and getting bolder about it as time goes on. We call that one dark energy. And here is the part that makes physicists go quiet at conferences. We are far more honest about the first one than the second. We can photograph a black hole now. We have never seen dark energy at all. We have only seen what it does. So that is the question we will be circling all night, softly, from many directions. Gravity only ever seems to pull things together. So how can the same universe contain places where it pulls so hard that nothing escapes, and at the same time be flying apart faster every year as if gravity were being overruled? How can the inward pull and the outward push both be true at once? Nobody set out to find either answer. Both arrived almost by accident, carried in on the backs of people who were mostly trying to solve something else entirely. And to understand how that happened, we have to go back a few centuries to a man sitting in the English countryside during a plague, watching the world fall. Let us go slowly into the past now. There is no hurry. We have plenty of night. The story of the inward pull really begins with a man named Isaac Newton. He was born in 1642 in a small stone farmhouse in Lincolnshire, in the east of England, into a family that fully expected him to grow up and manage sheep. He was not, by most accounts, a warm man. He was secretive, easily wounded, prone to long, silent grudges, and happiest when left completely alone with a problem. And in the years around 1665 and 1666, when a wave of plague closed the university at Cambridge and sent the students home, Newton went back to that quiet farmhouse and was left, for once, completely alone. Those 18 or so months are sometimes called his year of wonders, because in that stretch of forced isolation, he laid the groundwork for an astonishing amount of what came after. The story everyone knows, the apple falling in the orchard, is probably softened and simplified in the retelling. But there is a real idea buried in it, and the real idea is the thing that matters. Newton's leap was not noticing that the apple fell. Everyone had always known things fall. His leap was wondering whether the very same pull that brought the apple down might reach all the way up to the moon. Whether the moon, in its endless circle overhead, was in some sense also falling around the earth instead of straight onto it, held in place by exactly the same force that tugged the apple from the branch. That was the radical thought. Not that gravity existed, but that it was universal, that it was one law operating everywhere, on the small and the enormous alike, with no special rules for the heavens. When he finally wrote all this down, decades later, in a dense Latin book published in 1687 with the title Philosophiae Naturalis Principia Mathematica, he gave the world a single equation that described how any two objects in the universe pull on each other, from two dust grains to two galaxies. It worked breathtakingly well. It still does. We sent people to the moon using mathematics that Newton would have recognized. But notice something quiet about Newton's picture, because it will matter later tonight. In his world, gravity was a force that reached invisibly across empty space, instantly, from one body to another. Space itself was just an empty stage, a fixed and changeless container in which all the falling and orbiting happened. Time was a steady, universal clock, ticking the same everywhere. The stage did not bend. The clock did not vary. Things moved around inside the box of space. But the box itself was simply there, eternal and unmoving. For more than 200 years, that was the picture. and it was good enough for almost everything. It was so good that to question it seemed faintly absurd. The man who questioned it was born in the German city of Ulm in 1879, and his name was Albert Einstein. You have heard the name your whole life, so it can be hard to feel how strange his idea really was when it arrived. As a young man, he could not find an academic job and ended up working as a clerk in a patent office in Bern, in Switzerland, assessing other people's inventions while thinking, in the gaps, about light and time and motion. Out of that came one extraordinary year, 1905, where he published a series of papers that quietly rearranged physics. But the piece that matters most for us tonight came a decade later, in 1915, after years of grinding, frustrating mathematical work that he later said nearly broke him. It is called the general theory of relativity, and it did something almost no one expected. It took Newton's empty, eternal stage, the fixed box of space and the steady clock of time, and it brought them to life. Here is the thing, and I want to say it slowly because it is the hinge the whole night turns on. In Einstein's picture, space and time are not a fixed background. They are a single flexible fabric, woven together, that bends and stretches and sags in the presence of anything heavy. Mass does not reach across empty space to tug on other mass the way Newton imagined. Instead, mass curves the fabric of space and time around it, and other things simply follow the curve. Gravity, in this view, is not a force pulling across a gap. It is the shape of space itself. The Earth does not loop around the sun because a rope of force is yanking on it. It loops around the sun because the sun's great mass has bent the space nearby into a kind of valley, and the Earth is rolling along the inside of that valley the way a marble circles the inside of a bowl. There is no rope. There is only the shape. This is the place where, when I have walked people through it before, I can almost feel their eyes start to lose focus. So let me give you something to hold on to. Imagine a clean, taut bedsheet, pulled tight and held flat at each corner so it makes a smooth, level surface, about waist high. Now imagine setting a heavy ball, something like a cannonball, gently down in the middle of it. What happens? The sheet sags. It dips down into a smooth, funnel-shaped well, deepest right under the ball, and gradually flattening out as you move toward the edges. Now take a small marble and roll it across the sheet, near the ball, but not straight at it. The marble does not travel in a straight line. It curves. It follows the slope of the dip, swinging around the heavy ball, maybe circling it a time or two before it loses speed. Nothing reached out and grabbed the marble. The marble simply went where the bent surface led it. That sagging sheet is a flattened little picture of what mass does to space and time everywhere, all the time. The sun makes a deep, wide dip in the fabric, and the planets roll around inside it. The Earth makes a smaller dip, and the moon circles in that. You yourself, lying there right now, make a tiny dimple in the fabric of space and time, far too faint to feel, but real. Everything with mass leaves its mark. And once you see gravity this way, as the shape of space rather than a pull through it, a question starts to form on its own. A question that Newton's picture could never have raised. What if you took a piece of the fabric and pressed down on it harder and harder, with more and more mass packed into less and less room? How deep can the dip go? Is there a limit? Or could the fabric sag so steeply, so completely, that it folds in on itself and tears free from the rest? Hold that question in the back of your mind. We are going to come back to it, and when we do, we will have found the edge of a black hole. But first we need to meet the man who actually did the arithmetic. And to meet him, We have to go somewhere unexpected. We have to go to the trenches of the First World War. Within months of Einstein publishing his new theory in late 1915, a letter reached him from the Eastern Front. It came from a German astronomer named Karl Schwarzschild, who was, at that moment, a soldier in his early 40s, serving in the army and stationed near the fighting in Russia. Schwarzschild was not a young unknown. He was a respected scientist, the director of a major observatory back home. But he had volunteered out of a sense of duty, and there he was, in the cold and the mud, calculating artillery trajectories by day. And in whatever scraps of time he could find, he had taken Einstein's brand new equations, which were so difficult that even Einstein had only managed rough approximate solutions, and he had found an exact one. A clean, complete answer describing the curved space and time around a single round mass, like a star. There is something almost unbearably moving about this when you sit with it. A man in a war, surrounded by the very worst of what people do to each other, turning in his spare hours to the deepest and quietest question there is: the shape of space around a star. He sent his work to Einstein, who presented it to the Berlin Academy on Schwarzschild's behalf in early 1916, and who was genuinely astonished that such a clean solution existed at all. And then, just a few months later, Schwarzschild was dead. He had contracted a rare and painful autoimmune skin disease, possibly worsened by the conditions at the front, and he died in May of 1916 at the age of 42, having handed the world a piece of mathematics that contained, hidden inside it, the first real description of a black hole. He never knew what he had found. The full strangeness of it would not be understood for decades, because buried inside Schwarzschild's tidy solution was something that looked, at first, like a mistake. The equation said that for any given amount of mass, there was a particular distance, a particular radius, where something bizarre happened. If you could somehow crush all of that mass down into a sphere smaller than that critical radius, the curvature of space around it would become so extreme, the dip in the fabric so impossibly steep, that the maths seemed to break down entirely. Time appeared to stop. Distances seemed to stretch to infinity. At that special radius, the answers stopped making ordinary sense. For years, most physicists, including Einstein himself, simply assumed this was a flaw in the calculation, or a mathematical curiosity that could never happen in the real world. Surely, they thought, nature would never actually pack that much mass into that small a space. Surely something would stop it. But let us hold that thought and slow right down. Because before we can understand why nature does in fact do exactly that, and what it means when it happens, we need to build up the simple picture properly, one careful piece at a time. We need to talk about what it really takes to escape. Think about throwing a ball straight up into the air. It rises, it slows, it stops for a single suspended instant at the top of its arc, and then it falls back into your hand. Throw it harder and it goes higher before it comes back. There is a feeling everyone has had, as a child, of wondering what would happen if you could just throw it hard enough that it never came back down at all. And it turns out that is not a silly question. There is a real answer, a real speed, at which an object thrown upward would simply keep going, climbing away from the Earth forever, never falling back. We call that speed the escape velocity. For our planet, it works out to a little over 11 kilometers every second, which is roughly 25,000 miles an hour. Throw something that fast, straight up, ignoring the air, and it will leave the Earth behind for good. Now, here is the quiet thread that connects escape velocity to everything else. The escape velocity depends on two things, and only two things. It depends on how much mass is pulling, and on how close you are to the center of that mass. The more mass, the faster you have to go to get away. And the more tightly that mass is packed, the closer you can get to its center. And the closer you get, the steeper the climb, and the faster you have to be moving to make it out. So imagine taking the Earth and squeezing it. Not adding anything, not changing how much stuff is there, just compressing all of it into a smaller and smaller ball. The mass stays the same, but the surface, the place you would stand and throw your ball, creeps closer and closer to the center, down into the steepest part of the dip. And as it does, the escape velocity climbs. Squeeze the Earth down to the size of a marble, and the speed you would need to escape from its surface becomes enormous. So now follow the thought all the way to its end, gently, without flinching. Keep squeezing, keep packing the mass tighter, letting the escape velocity rise and rise. Is there a speed limit anywhere in the universe that this might run into? There is. There is one absolute speed cap that nothing can exceed, a wall woven into the fabric of reality itself. And it is the speed of light, just under 300,000 kilometers every second. Nothing carrying mass can reach it, and nothing at all, not even light, can go faster. So here is the question that Schwarzschild's equations were quietly asking. What happens if you squeeze a mass so small, so dense, that the escape velocity at its surface reaches the speed of light itself? The answer is the gentlest and most terrible thing. At that point, light can no longer escape. And if light cannot escape, nothing can, because nothing outruns light. You have made a region of space from which there is no return. Not because there is a wall, not because something is grabbing you, but simply because every possible path out now leads back in. The dip in the fabric has become a pit with no upward slope anywhere along its rim. This is the heart of what a black hole is. It is not a thing exactly, not a hole punched in space, not a cosmic vacuum cleaner roaming around sucking up stars, despite how the films like to show it. It is a place where so much mass has gathered into so small a space that the curvature closes over the top of itself, and an edge forms, an invisible boundary in empty space, beyond which every road leads inward and none lead out. That boundary has a name, and it is one of the loveliest and most precise pieces of language in all of science. We call it the event horizon. Think for a moment about why that word fits so perfectly. A horizon, the ordinary kind, the line where the sea meets the sky, is not a wall. There is nothing there. You can sail toward it forever and never reach a barrier. It is simply the limit of what you can see from where you stand. The event horizon of a black hole is exactly that, but for events instead of scenery. It is the line beyond which no event, nothing that happens, can ever send word back to the outside universe. Light from inside cannot reach you. A signal from inside cannot reach you. Even the information that something happened in there can never get out. It is a horizon for happenings. Whatever occurs on the far side of it is sealed off from the rest of everything forever. That word, black hole, by the way, is far younger than you might think, and it did not come from Schwarzschild or Einstein. For decades, these objects had clumsy technical names, things like collapsed stars or frozen stars. The short, dark, memorable phrase we use now was popularized by an American physicist named John Wheeler, who began using it in talks and writing around 1967. Wheeler had a gift for naming things, for finding the phrase that made a strange idea suddenly stick in the mind, and black hole stuck better than anything. Within a few years, It was everywhere. It is worth noticing how much a good name can do. The idea had existed in the equations for half a century, barely discussed, half believed. Give it 2 short words, and suddenly the whole world is thinking about it. So that is the inward pull, taken all the way to its limit. A black hole is gravity carried to its absolute extreme. The dip in the fabric of space made so deep and so steep that it folds shut over the top, sealing off a region of the universe behind a horizon no light can cross. And for a long time, this was where the strangeness was supposed to live. Out there, in the rare, violent deaths of enormous stars, in a few exotic corners of an otherwise well-behaved cosmos. Before we leave the black hole behind, though, let us linger for a moment on one of the strangest questions people always ask about them. Ask softly, the way you might wonder about something just before sleep. What would it actually be like to fall in? Not as a thing to fear, you understand? Only as a thing to imagine, the way you might imagine sailing off the edge of a very old map. Because the answer is far stranger than simply being crushed. And it gathers up almost every confusing thing about black holes into one slow, vivid picture. Imagine gently that you are falling toward a black hole, feet first. Now, gravity, remember, gets stronger the closer you are to the center. And because your feet are a little closer to the black hole than your head, your feet feel a slightly stronger pull than your head does. On Earth, this difference is far too tiny to notice. But near a black hole, where the curvature of space grows so steep, that small difference between the pull on your feet and the pull on your head becomes enormous, and then unbearable. You would be stretched, slowly at first and then violently, pulled longer and thinner, like a piece of warm taffy drawn out between 2 hands, or like a single drop of water elongating as it falls. Physicists, with their gift for the strangely homely image, actually have a real word for this. They call it spaghettification. The black hole does not crush you into a ball. It draws you out into a long, thin thread, stretched by the difference in pull between one end of you and the other. But here is the part that bends the mind most of all, the part that has to do with time, and it is the quietest strangeness of them all. Suppose someone you love is watching you fall in, from a safe distance far away, while you drift down toward the horizon. To them, watching, something uncanny happens. As you approach the edge, you appear to move more and more slowly. Not because you are slowing down from your own point of view, but because time itself, near that deep bend in space, runs slower as seen from outside. Your watcher sees your fall stretch out, slower and slower, your image growing dimmer and redder as the light climbing back out to them loses energy on the way. And in the end, they never actually see you cross the edge at all. From their distant vantage, you appear to freeze, hovering forever at the brink, fading slowly into darkness. Your final moment stretched across an eternity that from their side never quite arrives. This is why some of the earliest physicists, before they understood it fully, called these objects frozen stars. From the outside, things falling in seem to slow and stop and hang there forever, frozen at the threshold. And yet, from your own point of view, falling, nothing strange happens at the crossing at all. You would sail across that fateful edge smoothly, perhaps without even noticing the precise moment you passed the point of no return, the horizon slipping behind you as quietly as a doorway, even as the watcher behind you sees you hang there for all of time. 2 completely different stories of the same fall, both entirely true, depending only on where you stand. That is what the bending of time really means, taken to its extreme. And it is the same bending of time you remember, that sits quietly inside the device in your pocket. But now I want you to do the opposite of everything we have just done. We have been squeezing inward, focusing tighter and tighter on smaller and smaller regions, chasing gravity to its most concentrated point. Let us reverse that completely. Let us pull all the way back, past the black hole, past the dying star that made it, past the galaxy that star lived in, out past the neighboring galaxies, out and out until the largest things we know, vast islands of hundreds of billions of stars, look like nothing more than scattered specks of light drifting in the dark. Let us look not at one heavy object, but at everything at once, at the universe as a whole. Because when you do that, when you stop staring at the pits and start watching the whole fabric, you find that something is happening to it that has nothing to do with falling at all. The fabric is stretching. To feel why that was such a shock, you have to remember what everyone expected. If the universe is full of matter, and matter pulls on matter through gravity, then the natural expectation, the obvious one, is that everything should be falling together, slowly, over unimaginable spans of time. The gravity of all the matter in the cosmos should be drawing it inward, pulling the whole thing toward an eventual collapse, or at the very least slowing down any motion outward. Gravity only pulls, so a universe ruled by gravity should be a universe headed, eventually, toward togetherness. That is what the equations seem to demand. And it troubled Einstein deeply because the universe he believed he lived in, the universe nearly everyone believed in around 1917, was thought to be static, eternal, unchanging, neither growing nor shrinking, the same grand arrangement of stars sitting in place forever. But his own equations would not allow it. When Einstein applied general relativity to the entire universe, the maths refused to sit still. A universe full of matter, the equations insisted, could not simply hover in place. The gravity of all that matter would make it contract. It wanted to fall inward. And Einstein, convinced that the real universe was static and eternal, did something he would come to regret. He went back into his equations and added a new term by hand, a kind of counterweight, a built-in outward push spread evenly through all of space, tuned to exactly balance the inward pull of gravity and hold the universe still. He called this term the cosmological constant, and in the mathematics it is written with the Greek letter lambda. Its only job, as far as he was concerned, was to keep the universe from collapsing, to prop it up and hold it steady against its own weight. Let us slow down here, because this single decision is one of the most important and most human moments in the whole story, and it has a long tail that reaches all the way to the present. Einstein did not add the cosmological constant because the evidence demanded it. He added it because he could not believe the universe was anything other than eternal and unchanging, and his equations were telling him a story he did not want to hear. He forced the maths to agree with his expectation, and for a little while it seemed to work. The universe could be held static, balanced on a knife edge between collapse and expansion, by this carefully tuned outward push woven into the emptiness of space itself. But the balance was fragile, and the assumption underneath it was about to come apart completely, because out in the real sky, the universe was not standing still at all. We just did not have eyes good enough to see it yet. The eyes came, slowly, from a few different directions at once. First, there was a young Russian mathematician and meteorologist named Alexander Friedmann, who around 1922 did something Einstein had not. He took the equations of general relativity and asked, honestly, without any assumption that the universe must be static, what kinds of universes they allowed. And the answer, he found, was that the natural solutions were not static at all. They were universes that changed in time. Universes that could expand, growing larger as the ages passed, or contract, shrinking together, but almost never simply sitting still. Friedman was, in effect, telling Einstein that the cosmological constant was an unnecessary patch over a truth the equations had been trying to reveal. The universe, the math suggested, was supposed to be moving. Friedman died young, in 1925, of typhoid fever, at only 37, and did not live to see how completely right he turned out to be. Then, working separately and from a very different starting point, there was a Belgian named Georges Lemaitre. And here is a detail people often find surprising. Lemaitre was not only a physicist and astronomer, he was also an ordained Catholic priest. He wore the collar. He moved between the cathedral and the equations without apparent difficulty, treating them as two separate questions about two separate things. Around 1927, he independently worked out, like Friedman, that the equations described an expanding universe, and a few years later, he took one daring step further. He reasoned that if the universe is expanding now, growing larger as time goes forward, then running the film backward, the universe must have been smaller in the past, and smaller still further back. Push that logic all the way to its beginning, and you arrive at a moment when everything that exists was packed together into a single dense point, from which the whole expansion began. Lemaitre called it the primeval atom. The world would later give it a mocking nickname that stuck and lost its sting entirely. We call it the Big Bang. But ideas alone, however beautiful, do not settle anything in science. Someone had to actually look at the sky and measure whether the universe was truly expanding or not. And that brings us to a large new telescope on a mountain in California, and to a former lawyer and athlete with an enormous ego and an even more enormous instrument. His name was Edwin Hubble, and he worked at the Mount Wilson Observatory, perched above Los Angeles, using what was then the largest telescope on Earth, a 100-inch giant that could gather light from objects almost unimaginably faint and far away. Through the 1920s, Hubble and his patient, meticulous assistant Milton Humason, did two crucial things. First, they established beyond argument that the faint smudges of light astronomers had been cataloging for years were not clouds of gas inside our own galaxy, as many had assumed. They were entire separate galaxies, vast collections of billions of stars, lying at staggering distances far outside the Milky Way. In a single stroke, the universe became thousands of times larger than most people had imagined. And second, and this is the part that broke the static universe forever, Hubble measured how fast those galaxies were moving. Here is how he could tell, and it is a beautiful piece of detective work that uses something you may have noticed in everyday life without ever naming it. You know the way the sound of a passing train or an ambulance changes pitch as it goes by. As it races toward you, the whine rises, sharp and high. As it passes and races away, the pitch drops, sagging downward into a lower tone. The sound itself never changed. What changed is that the source was moving. Rushing toward you, each sound wave gets crowded a little closer to the one behind it, bunching up, raising the pitch. Rushing away, each wave gets stretched a little further from the next, spreading out, lowering it. The motion of the source squeezes or stretches the waves, and your ear reads that squeeze or stretch as a change in tone. Light does the very same thing, except that with light, we read the squeeze and stretch not as pitch, but as color. Light from an object rushing toward us gets crowded toward the blue end of the spectrum. Light from an object rushing away gets stretched toward the red end. Astronomers call that stretching toward red a redshift, and it is one of the most powerful tools they have, because the amount of redshift tells you exactly how fast something is receding. When Hubble measured the light from galaxy after galaxy, he found that almost all of them were redshifted. Almost all of them were moving away from us. And then came the detail that changed everything. The pattern hiding underneath the measurements. The farther away a galaxy was, the faster it was receding. Twice as far meant roughly twice as fast. 10 times as far, 10 times as fast. A clean, steady relationship announced in 1929 that we now call Hubble's law, though in fairness it should carry Lemaitre's name alongside it, since he had predicted exactly this 2 years earlier. Now, let us be very careful here, because this is precisely the place where people's intuition leads them astray, and I do not want you to carry away the wrong picture as you drift off. When you hear that all the galaxies are moving away from us, and the farther ones moving faster, it is terribly natural to imagine that we are sitting at the center of some great explosion, with everything blasting outward away from our special spot. That is not what is happening. That is not it at all. The galaxies are not flying apart through space, like shrapnel from a bomb scattering across an empty room. It is space itself that is expanding, stretching, growing larger between the galaxies, carrying them apart the way the surface of a balloon carries apart any dots you have drawn on it. And this distinction is the whole heart of understanding the universe. So let me give it the slow, careful analogy it deserves. Picture a loaf of raisin bread dough, sitting in a warm kitchen, beginning to rise. The raisins are scattered all through it, near and far. The dough is the space, and the raisins are the galaxies. As the dough rises and swells, it expands in every direction at once, uniformly, throughout its whole body. Now imagine you are a tiny observer sitting on one particular raisin, looking around at all the others. As the dough swells, every other raisin moves away from you, because there is more and more dough growing between you and each of them. And here is the key thing, the thing worth holding on to. A raisin that started out twice as far away from you will appear to move away twice as fast, because there is twice as much dough between you and it. And all of that dough is expanding. A raisin 10 times as far moves away 10 times as fast because there is 10 times as much swelling dough in between. That is Hubble's law, exactly, falling straight out of nothing more than the dough expanding evenly everywhere. And notice the most reassuring part of the picture. Your raisin is not special. It is not the center. If you hopped over to any other raisin in the loaf and looked around from there, you would see precisely the same thing. Every other raisin receding from you, the far ones faster than the near ones, all of them apparently fleeing from your new position. There is no center to the expansion, because the expansion is not happening at a point. It is happening everywhere, in all the dough at once. We are not at the middle of the universe. There is no middle, wherever you stand. The whole rest of it appears to be drifting away from you. And an observer on a galaxy 10 billion light years from here would see exactly the same view, with our galaxy among the specks fleeing into their distance. So the universe was expanding. The static, eternal cosmos was dead, and the cosmological constant that Einstein had added by hand to hold it still was no longer needed for anything. The universe held itself in motion all on its own, expanding outward gradually, just as Friedman and Lemaitre had said. And Einstein, to his credit, accepted the new picture once the evidence was in. He let go of his fixed universe. He removed the cosmological constant from his equations, set the troublesome lambda to 0. And in later years, he is often reported to have called the whole episode the biggest blunder of his life. He had let his expectation about how the universe ought to behave overrule what his own mathematics had been trying to tell him, and he had patched over a discovery he might otherwise have made. The lesson seemed clear. There was no mysterious outward push woven into space. There was just matter, and gravity, and an expansion that gravity would slowly, patiently work to slow down. The cosmological constant was a mistake, quietly buried, an embarrassing footnote in the life of a genius. Except it was not buried. It was only sleeping. And it was going to wake up decades later in the most unsettling way. And when it did, it would drag the strangeness of the whole night back into the open. But let us not rush there. Let us sit for a while in the comfortable middle of the 20th century when the picture seemed, for once, almost settled. The universe was expanding, born from a hot, dense beginning, full of galaxies drifting apart. Gravity was the only game in town, pulling everything together, gently fighting the expansion, slowing it down. The only real question that remained, people thought, was a question of fate, of how the story ends. And it was a clean question, almost geometric in its simplicity. Was there enough matter in the universe, enough total gravity, to eventually halt the expansion and reverse it, pulling everything back together into a final collapse? Or was there too little, so that the expansion would coast onward forever, slowing but never stopping, the galaxies thinning out into an ever colder, ever emptier dark? Think of it like throwing that ball into the air again, the way we did near the beginning of the night. You throw the ball up, gravity pulls it back. If you throw it slowly, it rises a little, stops, and falls back into your hand. Which is the collapsing universe, gravity winning, everything falling back together. If you throw it exactly at escape velocity, it climbs forever, slowing toward a crawl, but never quite stopping, just barely escaping, which is the universe that expands forever, but only just. Either way, in this whole picture, one thing is certain: the ball is slowing down. Gravity is always pulling back. The only question is whether the pull is strong enough to win. Nobody in this comfortable picture imagined for a single moment that the ball might be speeding up as it rose. That would be absurd. That would be like tossing a ball gently into the air and watching it accelerate toward the ceiling, faster and faster, as though some invisible hand were shoving it upward harder the higher it went. No one threw a ball expecting that, and no one studied the universe expecting that either. This is where we arrive at the turning point of the whole night, the moment the comfortable story shattered. And I want to set it up carefully, because it is one of the genuine surprises in the history of human knowledge. In the 1990s, two separate teams of astronomers set out to measure, with real precision, how quickly the expansion of the universe was slowing down. Notice the assumption built into the very goal. They were not asking whether it was slowing. Everyone knew it was slowing. Gravity guaranteed it. They were only trying to measure how much, because the rate of slowing would tell them how much matter the universe contained, and therefore how the story would end. It was, in their minds, a careful bookkeeping exercise. Difficult, demanding, but not revolutionary. They expected to fill in a number. To do it, they needed a way to measure enormous distances across the cosmos with great accuracy. And they found one in a particular kind of stellar explosion called a type Ia supernova. Without getting tangled in the details as you drift off, the important thing is this: these particular explosions are remarkably uniform. They go off with very nearly the same true brightness every time, like identical lighthouses scattered across the universe. And if you know how bright a lighthouse truly is, than by measuring how dim it appears from where you stand. You can work out exactly how far away it must be. The dimmer it looks, the farther it is. So these supernovae became cosmic measuring rods, beacons of known brightness flaring up in distant galaxies, letting astronomers measure distances across billions of light years. And by combining that distance with the redshift of the same galaxy, which told them how much the universe had expanded since the light left, they could reconstruct the history of the expansion itself. They could see how fast the universe had been growing at different times in the past. The two teams were led, between them, by three astronomers whose names you should hear, because they earned them. One team, the Supernova Cosmology Project, was led by Saul Perlmutter, working out of Berkeley in California. The other, the High Z Supernova Search Team, included Brian Schmidt and Adam Rees. Through the late 1990s, both groups gathered their distant supernova, measured their faint light with enormous care, and crunched the numbers, fully expecting to see the signature of an expansion that had been gradually breaking under the weight of all the matter in the cosmos. They expected the distant supernovae, whose light had traveled for billions of years from an era when the universe was expanding faster, to look a certain way. They expected, in short, to measure the deceleration. What they found in 1998 made no sense at all. The distant supernovae were too faint. They were dimmer than they should have been, which meant they were farther away than they should have been, which meant the universe had expanded more than anyone expected over those billions of years. And when both teams, working completely independently and half hoping the other would prove them wrong, chased the implication all the way down, they arrived at the same impossible conclusion. The expansion of the universe was not slowing down. It was speeding up. It had been slowing for billions of years, as everyone expected, gravity gently applying the brakes. And then, several billion years ago, it had turned a corner and begun to accelerate, growing faster and faster ever since. The ball, thrown into the air, was not falling back. It was not even coasting. It was rising faster every second, shoved upward by something nobody could see and nobody could name. Let that settle for a moment, because it really is as strange as it sounds. For most of the history of the universe, gravity had been doing exactly what gravity does, pulling all the matter together, slowing the expansion down. And then, at a certain point, something else took over. Some other influence, spread thinly through all of empty space, gentle but utterly relentless, began to win. Not by pulling things together, but by pushing space apart, and pushing harder as space grew larger, so that the more the universe expanded, the more strongly it was driven to expand still faster. The result earned both teams the Nobel Prize in Physics in 2011, shared between Perlmutter, Schmidt, and Rees. But the prize was for the discovery, not for the explanation, because there was no explanation. There still is not. All anyone could honestly say was that something was doing the pushing, and that they did not know what it was. So they gave the unknown thing a name, the way you give a name to a stranger you have only seen from across a room. In 1998, the physicist Michael Turner coined the term that has stuck ever since. He called it dark energy, and it is worth pausing on that word, dark, because it is being used in a very particular and very honest way. It does not mean evil, and it does not mean black or invisible in any ordinary sense. It means hidden from us, unknown. Dark the way an unlit room is dark, the way the far side of a question is dark. We call it dark energy for the same reason we earlier called those galaxies dark matter, which is a related but separate mystery. The word dark is a confession. It is physicists admitting plainly that they have found something real, something they can measure, something that makes up the great majority of everything there is, and that they have essentially no idea what it actually is. And here is the part that should make the back of your neck prickle, gently, as you lie there in the dark of your own room. When you add it all up, when you tally everything in the universe by how much it contributes to the total, ordinary matter, the stuff of stars and planets and people and this bed in your body, comes to only about 5%. Another roughly 27% is that other mystery, dark matter, some unseen substance that holds galaxies together but does not shine. And all the rest, around 68%, more than 2/3 of everything, is dark energy. The thing we cannot explain. We are living inside a universe that is overwhelmingly made of something we have never identified. A vast, invisible push that we know only by its effect on the drifting of distant galaxies. The familiar world, the world of touch and light and matter, is a thin, bright film floating on top of an enormous dark ocean whose nature is completely unknown to us. Now, here is where the night folds back on itself, where the buried thing wakes up. Because when the two teams found the acceleration, and physicists scrambled to describe it mathematically, the simplest description that fit the data was an old, familiar friend, one we thought we had put away forever. It was a constant outward push, spread evenly through all of space, never thinning out as the universe expanded, always there in every cubic meter of emptiness. It was, in other words, exactly the thing Einstein had invented in 1917 and then renounced as his greatest blunder. The cosmological constant, the lambda he had set to 0 and walked away from. It turned out he had been right to write it down and wrong only about its value and its purpose. It was not there to hold the universe still. It was there to push it apart, faster and faster, and he had thrown it away just decades too soon. The blunder, it seems, was not adding the constant. The blunder was taking it back out. Let us slow right down now and try to understand what this constant could possibly be, because this is where the deepest confusion in all of modern physics lives. And I want to walk you into it carefully, one gentle step at a time. The leading idea, the one most physicists reach for first, is that dark energy is the energy of empty space itself. And I know how that sounds. Empty space is supposed to be empty. That is what the word empty means. How can nothing have energy? How can a perfect vacuum, a region scrubbed clean of every particle and every speck of matter, push on anything at all? Here is where we have to gently set down our everyday idea of nothing, because the universe does not actually contain any such thing. According to quantum physics, which is our best account of how the very small behaves, a perfect vacuum is not truly empty. It is not a calm, still nothingness. On the tiniest scales, in the briefest moments, empty space seethes. Pairs of particles flicker into existence and vanish again almost instantly, borrowing energy from the vacuum and paying it back before the universe can quite notice. Space, at the finest level, is a restless, foaming, simmering thing, never truly at rest, never truly empty. And if all that ceaseless flickering carries energy, then empty space itself has energy, an energy that belongs to the vacuum, that exists wherever there is space at all, even where there is nothing else. Physicists call it vacuum energy. And a vacuum energy spread evenly through all of space would behave, in Einstein's equations, exactly like a cosmological constant. It would push space apart. The more space there is, the more vacuum energy there is, and so the harder the push, which is precisely why the expansion accelerates. It fits. It is elegant. It would tie dark energy directly to the deepest theory we have of matter and forces. And then you try to calculate how much energy the vacuum should have, and the whole beautiful picture detonates in your hands. This is the part I have to ask you to forgive me for, because it is genuinely uncomfortable, and it is the single largest unsolved embarrassment in all of physics. When physicists use quantum theory, the same theory that gives us lasers and computer chips and the most precisely confirmed predictions in the history of science, to calculate how much energy empty space ought to contain, they get a number. And when they compare that calculated number to the amount of dark energy we actually measure out in the universe, the two do not roughly agree, and they do not disagree by a little. They disagree by a factor so vast it is almost impossible to write down. The theoretical prediction is larger than the measured value by something like 10, followed by 120 zeros. That is not a small error. It is the worst quantitative prediction in the history of science, by an enormous margin. If the vacuum really had as much energy as the theory says it should, the universe would have torn itself apart so violently and so quickly that no galaxy, no star, no planet, no you could ever have formed at all. We wouldn't be here to be confused by it. And yet here we are, lying quietly in a universe held together far better than our best theory says it has any right to be. This towering, embarrassing gap has a name. It is called the cosmological constant problem, and it has loomed over theoretical physics for decades like a question no one can answer and no one can ignore. Why is the energy of empty space so absurdly, so improbably small, when everything we know says it should be colossal? Something must be canceling almost all of it out, with a precision so exact that it borders on the miraculous, leaving behind just the faintest residue, just enough to gently push the galaxies apart over billions of years, but not enough to wreck everything. Nobody knows what does the canceling, or why it stops where it does, or whether the question even has the shape we think it has. It is one of those problems that sits at the very edge of what we understand, where our finest theories, the ones that work flawlessly everywhere else, simply stop giving sensible answers. So, faced with that disaster, some physicists have wondered whether dark energy might not be a constant at all. This is where a second idea enters, with a name that sounds like it wandered in from medieval philosophy, which in a sense it did. The idea is called quintessence. The word comes from the old notion of a fifth element, the quinta essentia, beyond the ancient four of earth, water, air, and fire, a subtle fifth substance thought to fill the heavens. In its modern form, quintessence is the suggestion that dark energy is not a fixed property of empty space, but rather some new kind of field that fills the universe and can change over time. Not a constant, but something dynamic, something that might have been stronger or weaker in the past and might evolve in the future. If dark energy is a constant, its outward push is locked in forever, the same in every age. But if it is quintessence, then it is alive, in a sense. It moves. It could strengthen. It could fade. And which of those two it is, a dead, unchanging constant or a living, evolving field, makes all the difference to how the universe ends, which is a thread we will pick up before the night is over. I want to be very honest with you about where this leaves us, because the honesty is part of the strange comfort of it. We do not know what dark energy is. We can measure it with growing precision. We can describe its effects with equations that fit the data beautifully. We know how much of it there is, that it makes up more than 2/3 of everything. We know what it does, pushing space apart and accelerating that push. But its nature, what it actually is at bottom, remains one of the deepest open questions in all of science. It might be the energy of the vacuum, in which case we cannot explain why it is so small. It might be quintessence, a new field we have never directly detected. It might be a sign that Einstein's theory of gravity itself, which has passed every other test we have thrown at it, breaks down very gently on the largest scales and needs to be replaced by something deeper. We are, in the most literal sense, in the dark. Sit with that for just a moment, without any strain. More than 2/3 of the universe is a thing we have named only by its shadow, by the way it pushes the galaxies apart. We have built our whole understanding of everything on a foundation that is, in its largest part, unknown to us. And somehow, that is not frightening. It is almost the opposite. There is a kind of quiet thrill in it. The same feeling you might have had as a child standing at the edge of a dark wood, knowing it went on much further than you could see, and feeling not afraid but curious, drawn toward the depth of it. The universe is mostly mystery, and we are the small, curious creatures who have noticed, and that noticing is itself a kind of marvel. Now let us turn back, for a while, to the other mystery, the inward one, because black holes have their own deep confusions waiting, and the two sets of confusions, it will turn out, are quietly related. We left the black hole as a region sealed behind an event horizon, a place where the curvature of space folds shut and nothing escapes. But that simple picture hides a problem at the very center, and another at the very edge, and both of them have kept physicists awake for half a century. Let us go first to the center, the place at the very bottom of the pit. When a great star runs out of fuel and can no longer hold itself up against its own gravity, it collapses. And if it is heavy enough, nothing in nature is able to stop that collapse. The matter falls inward, and according to the plain reading of Einstein's equations, it does not stop at the size of a planet or a city or a grain of sand. It keeps falling, all of it, into a single point of zero size and infinite density. Physicists call that point a singularity. And the word is, in truth, an admission of defeat. A singularity is not a thing we understand. It is the place where our equations produce infinities, where density becomes endless and curvature becomes endless. And an infinity in a physical theory is almost always a sign that the theory has been pushed past its limits and broken. We do not believe there is really a point of infinite density at the heart of a black hole. We believe, instead, that something else takes over down there. Some deeper law we do not yet possess, a theory that would join Einstein's gravity to the quantum rules of the very small. We have been trying to write that theory for the better part of a century. We do not have it. The center of a black hole is, quite literally, a place where our knowledge runs out. Now let us go from the center to the edge, to the event horizon itself, and meet the most surprising idea of all, the one that ties black holes back to the vacuum and the emptiness of space, and so back to dark energy. For a long time, everyone assumed that black holes were perfectly black. That was the whole point of them. Nothing escapes, so they emit nothing. So they are utterly dark, growing only, never shrinking, eternal traps that swallow and never give back. And then, in 1974, a young British physicist named Stephen Hawking, working at Cambridge and already living for years with the illness that would gradually take away almost all movement from his body, did a calculation that astonished everyone, including himself. He combined the curved space of a black hole's edge with that restless quantum foaming of the vacuum we talked about earlier, the constant flickering of particle pairs into and out of existence. And he found something nobody expected. Black holes are not perfectly black after all. They glow, very faintly, but they glow, leaking a thin trickle of radiation out into the universe. And that trickle means they very slowly lose mass. And that means, given enough time, they evaporate. They die. The way it happens is so delicate, it almost sounds like a magic trick. So let me give you the gentle version. Remember that empty space, even right at the edge of a black hole, is constantly producing fleeting pairs of particles, one of matter and one of antimatter, that normally find each other again and vanish in an instant, paying back their borrowed energy. But right at the event horizon, something can go wrong with that quick accounting. One member of the pair can fall across the horizon, lost forever inside the black hole, while the other escapes outward into the universe before they can reunite. The escaping particle carries energy away. And because energy and mass are two faces of the same thing, that lost energy is paid for, in the end, out of the mass of the black hole itself. So the black hole, drop by infinitesimal drop, shrinks. Over time it gives back, as faint radiation, everything it ever swallowed, until at last there is nothing left, and it winks out entirely. We call that faint glow Hawking radiation, and it remains one of the most beautiful results in physics, even though for any real black hole, the effect is so unimaginably slow that we have never observed it, and likely never will directly. Now hold on to that, because here is the bridge between our two mysteries, and it is the loveliest part of the whole night. Hawking showed that a horizon, the edge of a black hole, is not a cold, dead, inert boundary. It has a temperature. It glows. It behaves, in a deep mathematical sense, like a warm object, with all the properties that warmth carries. And then physicists asked a quiet, daring question. If the event horizon of a black hole behaves this way, what about other kinds of horizons? Because dark energy, it turns out, creates a horizon of its own. In a universe expanding faster and faster, driven apart by that relentless outward push, there is a limit to how far we can ever see. Beyond a certain distance, space is being carried away from us faster than light can cross the gap. And so light from out there can never reach us, and never will. That distance is a horizon too, a cosmological horizon, the largest version of the same idea. It is the edge of everything we can ever know, drawn not by a black hole's mass, but by the expansion of the universe itself. And in the 1970s, two physicists, Gary Gibbons and that same Stephen Hawking, showed that this cosmological horizon, the boundary of the visible universe in an accelerating cosmos, has a temperature too. It glows faintly, just as a black hole's horizon does. The two horizons, one wrapped tightly around a collapsed star, the other wrapped around the entire observable universe, turn out to obey the same deep mathematics. The inward pull at its most extreme and the outward push at its largest scale meet in this single idea. The idea that a horizon, any horizon, the edge of what can never reach you, carries a temperature and a glow and a strange kind of warmth woven out of the quantum foam of empty space. The black hole and the dark energy, the pit and the expansion, the falling and the fleeing, are speaking, it seems, the same hidden language. We do not fully understand that language yet, but we can hear that it is one language, and not two. Here's the thing that I find quietly moving about all of this. For most of the 20th century, both of these things, black holes and dark energy, lived almost entirely on paper. They were solutions to equations, arguments at chalkboards, possibilities that many serious people doubted were real at all. Einstein himself did not believe black holes truly existed in nature, right up until his death in 1955. He thought, like many others, that something must always intervene to prevent that final, total collapse. And the cosmological constant was, for decades, treated as a dead idea, a mistake to be embarrassed about. Both ideas spent long years out in the cold, dismissed, marginal, half-believed. And then, within a few decades of each other, both came roaring back into reality, dragged out of the equations and into the observable sky by better instruments and patient, careful measurement. For black holes, the evidence built slowly and then suddenly. Through the 1960s and 1970s, astronomers found objects in the sky that made no sense unless something incredibly dense and dark was lurking there, unseen, betraying its presence only by its gravity, by the violent glow of matter spiraling in toward it. One of the first strong candidates, discovered through its powerful X-ray emission, carried the unromantic name Cygnus X1, a source in the constellation of the Swan where a visible star appeared to be orbiting something invisible and immensely heavy. For years, it was the subject of a famous friendly bet between Stephen Hawking and the American physicist Kip Thorne over whether it truly contained a black hole. Hawking, in a kind of insurance policy against his own hopes, bet that it did not. He eventually conceded the bet, acknowledging that the evidence had become overwhelming. But the proof that silenced nearly all remaining doubt came much more recently. And it came in two extraordinary forms within a few years of each other, both of which you were alive to witness. In 2015, a vast and exquisitely sensitive instrument called LIGO, built across two distant sites in the United States, detected something that Einstein had predicted a full century earlier and assumed could never be measured. Ripples in the fabric of space and time itself, gravitational waves, set off by two black holes spiraling together and merging far across the universe more than 1 billion years ago. As those two black holes whirled into each other and became one, they shook the fabric of space-time. And that shaking spread outward across the cosmos as a wave, stretching and squeezing space ever so slightly as it passed, until at last, on a September morning in 2015, it rippled through two detectors on Earth and was caught. We had heard for the first time the sound of black holes colliding, written into the trembling of space itself. And then, in 2019, came the picture. A planet-spanning network of radio telescopes, linked together to act as a single instrument nearly the size of the Earth, in a project called the Event Horizon Telescope, produced the first direct image of a black hole's shadow. The dark silhouette of the event horizon set against the bright glow of hot gas swirling around it, in the heart of a galaxy called M87, some 55 million light-years away. After a century of equations and arguments and doubt, after Schwarzschild scribbling in the trenches and Wheeler coining the name and Hawking conceding his bet, we finally simply looked, and there it was. A ring of light around a circle of absolute darkness. Exactly as the mathematics had always said it must be. A few years later, the same network gave us a picture of the far closer but much smaller black hole that sits at the center of our own galaxy, the Milky Way. A giant 4 million times the mass of our sun, around which the whole vast wheel of our home galaxy quietly turns. So both of these mysteries, the pit and the expansion, made the same journey, from a strange term in an equation to a possibility most experts doubted, to a measured, photographed, undeniable feature of the real universe we live in. And both of them, having become real, still hold at their hearts a confusion we cannot resolve. The black hole hides a singularity where our equations break, and at its edge a faint glow that may carry a paradox about information we have not fully untangled. The dark energy hides a vacuum whose energy we cannot calculate, and a question about its own nature we cannot answer. The strangeness did not go away when the objects became real. The strangeness simply moved deeper, retreated to the very center and the very edge, to the places where what we know finally gives out. Let us pause here and let the pieces settle into place, because I think there is a way of seeing all of this that makes the confusion feel less like chaos and more like a single shape we are slowly tracing in the dark. Take a slow breath and let me draw the whole thing together gently. Everything we have talked about tonight comes from one source, not from two unrelated discoveries, but from a single idea Einstein had in 1915. The idea that gravity is the shape of space and time, that mass and energy bend the fabric, and that everything else simply follows the bending. From that one idea, you get all of it. Push the bending to its extreme in one small place, and you get a black hole, a pit so steep it closes over itself. Apply the same idea to the whole fabric at once, and you find it cannot sit still, that it must expand or contract. Add the strange possibility that empty space itself carries energy, and you find the expansion can accelerate, driven apart by the very emptiness it contains. The pit and the expansion are not two separate marvels that happen to share a universe. They are the same fabric, the same equations, the same idea, expressed at the smallest extreme and at the largest. When you see them that way, the two mysteries stop feeling like a crowded museum of unrelated oddities and start feeling like two views of one strange, beautiful thing. And here is what I find genuinely reassuring, the thought I would most like you to carry off into sleep. The not knowing is not failure. It is the front edge of understanding. Every one of the people we have met tonight stood, in their own time, exactly where we stand now, holding an equation that worked and a meaning they could not grasp. Schwarzschild found the radius and thought it must be a flaw. Einstein found the constant and threw it away. The 1998 teams found the acceleration and could only give it a name that means we do not know. This is simply what the deep frontier looks like, from the inside. It does not look like triumph and certainty. It looks like a clean, confirmed measurement sitting next to a question no one can yet answer, and a patient willingness to hold both at once, for years, for decades, without forcing a false resolution. That patience, that comfort with the unfinished, is the quiet engine underneath all of it. There is one piece of the puzzle I have only touched lightly, and I want to give it a moment, because it ties the deepest confusion of the black hole to the deepest confusion of the vacuum, and it is genuinely unresolved to this day. When Hawking showed that black holes slowly radiate away and eventually vanish, he raised a troubling question. Everything that ever fell into the black hole, all the matter, all its detail, all the information about what it once was, seems to disappear when the black hole finally evaporates, leaving behind only that featureless, characterless glow. But a bedrock principle of physics, one that almost everything else depends on, says that information can never be truly destroyed. The universe is supposed to keep a perfect, if scrambled, record of everything that happens. So which is it? Does the black hole erase the past completely, violating one of the deepest rules we have? Or is the information somehow encoded, in some way we do not yet understand, in that faint escaping radiation, preserved after all? This is called the black hole information paradox, and physicists have argued about it fiercely and productively for nearly 50 years. There are promising recent ideas, threads that suggest the information does survive, woven subtly into the radiation in ways the original calculation missed. But it is not settled. It remains an open door at the very edge of what we know, the place where gravity and the quantum world meet and refuse, so far, to fully agree. I tell you that not to leave you with a worry, but because I think it is one of the most hopeful things about being alive right now. These are not closed books. The story is still being written by people working today in offices and observatories around the world, some of them perhaps awake at this very hour in their own time zone, staring at the same questions. You and I happen to be living during the chapters where these things were first measured, first photographed, first heard as ripples in space. We are not at the end of the story. We are somewhere in the patient, unhurried middle of it. Now, let us take that long view all the way out. Because if dark energy keeps doing what it is doing, the universe has a future, a very long and very strange future, and there is something deeply peaceful about following it to the end. Settle in. This is the slowest and largest part of the whole night, the part where time itself stretches out beyond anything our minds were built to hold. Right now, the night sky above your roof is full. There are stars, there are other galaxies. There is the soft band of the Milky Way, if you are far enough from the city lights. The universe, at this moment in its life, is rich and crowded and luminous. But dark energy is patient, and it does not stop. As space keeps expanding, faster and faster, the distant galaxies are being carried away from us at ever-increasing speed. And here is the quiet, lonely consequence. One by one, over enormous spans of time, those distant galaxies will be swept so far away, receding so quickly, that their light will no longer be able to cross the growing gap to reach us. They will redden and dim and fade, and finally slip beyond our cosmological horizon, out of view forever. Not because they have gone anywhere, but because the space between us has stretched too far and too fast. The universe will appear, from any one spot, to be slowly emptying. Far in the future, beings living in our own galaxy, or what it will have merged into, may look out at a sky that holds only their own island of stars, surrounded by an apparently endless and featureless dark, with every other galaxy long since vanished over the edge of the visible. They would have no way of knowing, from observation alone, that a vast universe of galaxies had ever existed at all. The evidence will have receded beyond reach. There is something almost unbearably gentle and sad about that picture, and yet it is what our best understanding predicts. If dark energy is the steady, unchanging constant it appears to be, the universe does not end in a bang or a crunch in this version of the story. It ends in a long, slow thinning out, a quiet drifting apart, a fading of the light. The stars themselves will eventually exhaust their fuel and go dark, the last of them flickering out across spans of time so long that the numbers stop meaning anything to us. And the black holes, those great patient pits, will be the very last structures left, having grown enormous, swallowing what remains. And then, across timescales so vast that the word unimaginable does not begin to reach them, even they will do what Hawking showed they must. They will glow, ever so faintly, and shrink. And after a stretch of time so long that you could write the years as a 1 followed by 100 zeros and still fall short, even the greatest black holes will evaporate entirely, releasing their last whisper of radiation into a cold and nearly empty space. This far, far future is sometimes called the heat death. A universe spread thin and cold and even, all its structure gone, all its energy smoothed out into a faint, uniform warmth approaching the absolute still of zero. It is the quietest possible ending, not a catastrophe, a settling. But remember the other possibility, the one that waits if dark energy is not a constant, but the living, changing thing called quintessence. If dark energy were to grow stronger over time, its outward push intensifying rather than holding steady, then the ending changes entirely, and it changes into something far more dramatic. The accelerating expansion would grow so fierce that it would begin to overwhelm not just the space between galaxies, but the forces holding galaxies themselves together, and then the forces holding stars and planets together, and at last the very bonds holding atoms together. In that scenario, sometimes called the Big Rip, the expansion would tear everything apart, from the largest structures down to the smallest, in a final accelerating shred of all that exists. Most current measurements suggest this is not the likely path, that dark energy looks reassuringly constant and steady. But we do not know for certain, and that uncertainty is exactly why telescopes are being built right now, this very decade, to measure dark energy more precisely than ever before, to find out whether it is the calm, eternal constant or the restless growing field, and so to learn which of these long endings the universe is quietly heading toward. I do not tell you any of this to disturb your rest, and I want to be clear about that as you lie there. These timescales are so far beyond a human life, beyond the life of our species, beyond the life of our sun, that they belong to a category of time that has nothing to do with you or me or anyone we will ever know. Our sun has billions of years left to shine warmly over the Earth. The fading of the galaxies lies trillions of years beyond that. These are not events to fear. They are simply the far shore of a very long story. And there is a particular kind of peace in knowing the shape of the whole thing. The way you can feel calm watching the tide go out, knowing it will be hours yet, and that you are warm and dry and far up the beach. Let us come back now, from those distant shores, all the way home, to your room, to this moment, to the present. Because it is easy to think of black holes and dark energy as things that have nothing to do with ordinary life, that live only out in the depths and the far future, untouchably remote. And in one sense, that is true. But in another sense, the very ideas that gave us black holes and dark energy are woven quietly into the texture of your everyday world, in ways you would never guess. Think for a moment about the small device that knows where you are, the one that guides you through an unfamiliar city, that finds the nearest place to eat, that tells you, to within a few steps, where on the surface of the Earth you happen to be standing. That gentle blue dot on a map relies on a fleet of satellites orbiting high above the planet, each carrying an extraordinarily precise clock, and each constantly broadcasting the time. Your device listens to several of them at once and works out its position from the tiny differences in when each signal arrives. But here is the thing that connects it to everything we have talked about tonight. Those satellite clocks, up there in orbit, do not tick at the same rate as the clocks down here on the ground. They cannot, because of exactly the ideas Einstein gave us. Time runs at slightly different rates depending on how fast you are moving and on how deep you sit in the curvature of space, in the dip made by the Earth's mass. The satellites, high up where the curve is gentler and moving quickly through their orbits, experience time passing at a measurably different rate than we do down here in the deeper part of the dip. If the engineers who built that system had ignored this, if they had assumed time was the simple, universal clock that Newton imagined, the whole system would drift hopelessly out of accuracy within hours, and your blue dot would wander off by miles. It works, it stays accurate, only because the people who designed it built Einstein's curved space and time directly into the calculations, correcting for the fact that the satellite's clocks run differently because they sit in a shallower part of the gravitational dip. So every single time you use that little map to find your way, you are, without knowing it, relying on the very same theory that describes the event horizon of a black hole, and the expansion of the whole universe. The bending of time near a mass, the thing that becomes infinite and terrible at the heart of a black hole, is the same gentle bending that, accounted for carefully, lets you find a coffee shop in a strange town. It is the same idea, scaled all the way down to the practical and the daily. There is something quietly lovely in that, I think. The deepest theory we have is not locked away in the heavens. It is in your pocket. And the work of understanding goes on, right now, in our own time, with instruments more powerful than anything the people we met tonight could have dreamed of. There is a space telescope, launched at the very end of 2021 and carrying the name James Webb, sitting 1.5 million kilometers from Earth, peering back across almost the entire history of the universe, gathering the faint, stretched, red-shifted light of some of the very first galaxies that ever formed, light that left them more than 13 billion years ago. There is another spacecraft, called Euclid, launched in 2023 by the European Space Agency, whose entire purpose is to map the shapes and positions of billions of galaxies across a huge swath of the sky, precisely in order to measure how dark energy has shaped the expansion of the cosmos over time, to learn whether it is truly the steady constant or the restless field. There is a great new observatory built on a mountaintop in Chile, designed to photograph the entire visible southern sky over and over, night after night, watching for the supernovae and the subtle patterns that will pin down dark energy more tightly than ever. The instruments that found these mysteries were the 100-inch telescope on Mount Wilson and the careful supernova surveys of the 1990s. The instruments that may finally explain them are switching on right now, in these very years, while you and I are alive to watch. That is worth sitting with for a moment as the night deepens. We tend to imagine that the great discoveries belong to the past, to the famous names in the textbooks, to people long dead. But the questions we have walked through tonight are open questions, live questions, questions whose answers may arrive within the lifetimes of people listening to this. Somewhere, right now, in some time zone where it is the middle of a working day rather than the middle of the night, there are people poring over the data streaming down from Euclid, or the images from Webb, or the nightly flood of measurements from that mountain in Chile, hunting for the faint signature that will tell us, at last, what dark energy is. And somewhere else, there are physicists filling chalkboards with the mathematics that might finally join Einstein's gravity to the quantum world and tell us what truly sits at the center of a black hole, where our equations now simply stop. The story is not finished. It is being written in the present tense. And think, too, about how much had to come together for us even to ask these questions properly. It took Newton's insight that the heavens and the earth obey one law. It took Einstein's leap that gravity is the shape of space and time. It took Schwarzschild's exact solution, found in a war. It took Friedman's honest mathematics and Lemaitre's daring backward reasoning to a beginning. It took Hubble's patient measuring of the fleeing galaxies. It took Wheeler's gift for a name and Hawking's astonishing glow at the edge of the dark. And the relentless, careful work of Perlmutter and Schmidt and Rees measuring the faint light of exploding stars across billions of years. Each of them added one piece. None of them saw the whole picture in their own lifetime. Each handed their piece forward to the next, the way you might pass a candle along a line of people in a dark room. No single person lighting the whole space, but the light traveling steadily down the line all the same. That is what understanding actually is. Not a single flash of genius, but a long, patient relay across centuries, carried by ordinary people who happen to care enough to add their one careful piece and pass it on. There is a deep humility in it, and a deep comfort too. The universe is far larger and stranger than any of us can hold in a single mind. More than 2/3 of it is something we cannot name. At the hearts of its black holes, our finest equations dissolve into infinities we do not trust. We are surrounded, in every direction and on every scale, by genuine mysteries, real and confirmed and unsolved. And yet, here we are, small, soft creatures on a small, wet planet, having figured out as much as we have, having weighed the invisible and photographed the edge of the inescapable, and heard the collision of black holes written in the trembling of space. We do not know everything. We do not know most things. But what we have managed to learn by passing the candle carefully down the long, dark line is genuinely astonishing. And it was won not by certainty, but by a patient willingness to sit with not knowing, exactly the way you are sitting quietly now in the dark, comfortable with the question, in no hurry for the answer. Let us circle back, slowly, one more time, over the two great ideas of the night, now that we have walked all the way around them. There is no new information coming. We are simply going to retrace the shape of it gently, the way you might run your hand along a familiar railing in the dark, just feeling the curve of something you already know, letting it settle deeper as your breathing slows. The first idea is the inward one. Gravity is not really a force pulling across empty space the way it once seemed. Gravity is the bending of space and time around anything that has mass. The earth bends it a little. The sun bends it more. And if you gather enough mass into a small enough space, the bending becomes so steep that it folds shut over the top of itself, sealing off a region behind an edge that no light can cross. That is a black hole. Not a thing reaching out to grab, not a hole torn in the world, but a place where the shape of space has closed around itself so completely that every road leads inward. At its center, our equations give out. At its edge, it glows ever so faintly. And over spans of time beyond all imagining, it slowly fades away. The most extreme expression of the oldest, most familiar force there is. The same force that takes a spoon to the kitchen floor. The second idea is the outward one, and it is in a way the mirror image of the first. Take that same bending fabric of space and time, but now look not at one heavy spot, but at the whole thing at once, the entire universe. And what you find is that it cannot sit still. It is expanding, growing larger, carrying the galaxies apart from one another, the way rising dough carries apart the raisins inside it. And not only is it expanding faster and faster, driven by something hidden in the emptiness, some energy belonging to space itself that pushes ever outward and grows stronger as space grows larger. We call it dark energy, and the word dark is an honest confession that we do not know what it is. It is more than 2/3 of everything there is, and it is a stranger to us. The most extreme expression of emptiness, the push hidden inside the nothing, the inward pull and the outward push, the pit and the expansion, the falling and the fleeing. Two faces of the same fabric, the same equations, the same single idea, expressed at the smallest extreme and the largest. And both of them, having begun as marks on paper that serious people doubted, are now measured, photographed, confirmed, woven into the real universe we actually live in. And both of them, at their very deepest, still hold a question we cannot answer, a place where our knowledge runs out and the frontier begins. That is not a flaw in the story. That is the story. The not knowing is simply the edge of the known. And the edge of the known is exactly where everything interesting has always lived. Now think about this softly as you lie there. You are resting right now on the surface of a planet that is itself sitting in a gentle dip it has made in the fabric of space and time. The Earth is curving the space around you very slightly, in every direction, and you are simply following that curve, held to the bed by the same shape of space that holds the moon in its orbit overhead. And the whole of it, the bed and the room and the planet and the sun and the galaxy, is being carried with everything else on the slowly stretching fabric of an expanding universe, drifting away from all the distant galaxies at this very moment, the space between us and them growing, patiently even now, even in the time it takes to breathe in and breathe out once. You are not separate from any of this. You are not a spectator looking at the universe through a window. You are made of it. You are a small, warm, breathing part of the very fabric we have spent the night tracing, lying still while the whole thing moves around you and through you and carries you along. There is a strange peace in that, I think. To know that the same theory that describes the most violent and extreme places in existence, the black holes and the expanding dark, is the very same theory that describes the gentle pressure of the bed against your back, the steady downward settling of your body into rest, the soft pull that keeps you here and lets you let go. It is all one thing, the terrible and the tender, the cosmic and the intimate, the falling spoon and the fleeing galaxy. One fabric, one idea, and you, resting quietly inside it. We have covered a great deal of ground tonight, and you do not need to hold any of it. Let it loosen. The names, the dates, the numbers, the careful explanations, let them all drift now, the way the galaxies drift, gently apart, carried off on the slow expansion of sleep. You do not have to keep any of it. It will keep itself. The universe will go on bending and expanding whether you remember a single word or not. And the people who study it will go on adding their careful pieces to the candlelit relay, in their offices and observatories, in whatever time zone the sun happens to be touching now. None of it asks anything of you tonight. It only asks you to rest. I want to spend these last quiet minutes simply being grateful, in a soft and unhurried way, for the people who made tonight's story possible. And then I will let you go down into sleep. Think of Isaac Newton, alone in a plague-emptied farmhouse in the English countryside, wondering whether the apple and the moon obeyed the same law. Think of Albert Einstein, who could not find a job and sat in a patent office in Bern, turning over the nature of space and time in the gaps between assessing other men's inventions, and who years later gave us the idea that gravity is the shape of the world itself. Think of Karl Schwarzschild, finding the first exact description of a black hole while serving as a soldier in the cold and mud of the Eastern Front, sending it to Einstein in a letter, and dying just months later without ever knowing what he had found. Think of Alexander Friedmann, the young mathematician who saw that the universe could not sit still, gone from typhoid at 37. Think of Georges Lemaitre, the priest who reasoned backward to a beginning, moving easily between the cathedral and the chalkboard. Think of Edwin Hubble and his patient assistant Milton Humason, measuring the fleeing of the galaxies night after night on a cold mountaintop above Los Angeles. Think of John Wheeler, who gave the dark pit its perfect short name. Think of Stephen Hawking, whose body grew steadily more still over the decades, even as his mind ranged out to the very edge of the black hole, and found, against all expectation, a faint glow there. Think of Saul Perlmutter and Brian Schmidt and Adam Rees, who set out merely to measure how fast the universe was slowing down, and instead discovered that it was speeding up, and so handed us the deepest mystery of all. None of them knew the whole story, Each of them carried the candle a little further down the long, dark hall and passed it to the next pair of hands. And the light is still moving down that hall, right now, tonight, carried by people you will never meet, in rooms lit at strange hours all around the turning earth. And think, finally, of every person who has ever simply lain back and looked up at the night sky and felt that particular mixture of smallness and wonder. The feeling that is older than any of the science, older than the names and the equations, as old as the first human who ever tipped their head back in the dark and felt the depth of it. That feeling is the beginning of everything we talked about tonight. Before the mathematics, before the telescopes, there was only that. A person, looking up, wondering. You have done it yourself, surely, on some clear night. That quiet lifting of the chest, that sense of the enormous, gentle dark overhead. Everything else, all the centuries of careful work, grew out of that simple human act of looking up and wanting to understand. And you are part of that long line too, just by listening, just by wondering alongside me here in the dark. So let us bring it all the way home now, into this room, into your body, and let the rest of it go. Feel the weight of yourself against the bed. Feel how the earth holds you there, gently, with the same curving of space that keeps the planets in their orbits, asking nothing of you but to settle and to stay. Let your shoulders soften down away from your ears. Let your jaw unclench. Let your hands lie open and loose. There's nothing left to follow tonight, nothing left to understand, nothing to remember. The thinking part of the night is over. You can set it all down now, the way you would set down something you had been carrying for a long way and were glad to finally rest. Let your breathing slow on its own. Do not steer it. Just notice it. The soft rise, the soft fall, like the slowest possible tide, in and out. Each breath a little quieter than the one before. You are a small, warm gathering of the same fabric we traced tonight, all the way out to the edge of the visible. And right now, that fabric is calm, and you are calm. And there is nowhere you need to be, and nothing you need to do. Far away, the galaxies are drifting gently apart, carried on the slow expansion of space. And it asks nothing of you. The black holes are turning quietly in the dark, glowing so faintly that the light will outlast the stars. And it asks nothing of you. The whole vast, patient universe is going about its long, slow work, expanding, bending, fading by degrees toward its distant and untroubled end. And not one bit of it needs anything from you tonight. It will all still be here in the morning. It will all still be here long after every morning any of us will ever see. You can let it carry on without you for a while. So let your mind go soft and dark and quiet, like the space between the stars. Let the last of the words dissolve. Let the names drift off, and the numbers, and the whole long story, until there is only the warmth of the bed, and the slow tide of your breath, and the gentle hold of the earth keeping you exactly where you are. Rest now. The universe is vast and old and strange, and you are a small, quiet part of it, safe and warm and held, drifting gently down into sleep. Rest. There is all the time in the world.